In this section, we're going to talk about calculating magnetic field with Ampere's law. So there's going to be quite a few applications for this in terms of practice problems at the very end. So let's first say that Ampere's law allows us to treat certain magnetostatic problems involving symmetry to obtain the value of the magnetic field B. So steps to applying Ampere's law. There's essentially three main steps. Number one is to recognize symmetry and sketch magnetic field lines. So remember in Gauss' law, we had to try and find symmetry in terms of a Gaussian surface. So here we want to think of a mathematical loop where we can guarantee the magnetic field B is either one of two things. It's either fully parallel to DL, or the field lines, or fully perpendicular to DL in areas that are not parallel. So very similar to Gauss' law, remember, we were able to determine E dotted with ds. We wanted those to be either fully perpendicular or fully parallel because we're looking at the total flux. But here we're looking at the total closed path. So we have to make sure that for the path itself can be broken up into different segments, but each of those segments must be either fully parallel so that all of the magnetic field is counted for, or fully perpendicular. So that's very important to understand that the analogies between the two, because they're very similar. So what this means is if we can confirm that your magnetic field B is either fully parallel or fully perpendicular, it means that we've accounted for 100% of the magnetic field, and therefore this means that B is a constant that we can factor out. So then the integral of B dotted with dl is equal to mu naught I enclosed becomes B integral of dl is equal to mu naught I enclosed, but we can also represent I enclosed as the integral or surface integral of J dotted with ds. So that's basically step number one, being able to recognize the symmetry and sketch magnetic field lines, and most importantly, pick an Amperian loop that will allow you to factor out your B. Number two, once you can factor out your B, you can just rearrange and solve for the magnitude of B. So that means B is equal to mu naught I enclosed over the integral of dl, Or if you choose to use the volume current density form, you have mu naught integral of j dotted with ds over the integral of dl. Last but not least, your magnetic field is a vector, so therefore you have to determine the direction of B by inspection. So that is where the right-hand thumb rule comes in handy, and we'll be going through several practice problems so that you can familiarize yourselves with applying these steps.